Okay, welcome to this new class. In the last class, we discussed about show that means we have a S and T are two transformation. We have a S and T are two linear transformation. Then we show that S T is equal to some identity, and we have a T of S is also identity. So now we have to just say that when we say that, and also show that S is equal to, you have a T inverse, and T is equal to, you have a S inverse in the last class. Okay, in this class we start with the motivated by this ST is equal to identity and T is equal to identity. We can define an invertible linear transformation. We already inverse transformation defined previously, but by this way we can also define inverse transformation. Let V and W be a two vector spaces, and let V from T from V to W be a linear transformation. If there exists a linear transformation S W to V, so we can simply say that we have a V to W, we have a T transformation, and W to V we have a S transformation. Then we have this is a ST, and this is ST is nothing but is equal to, we have a is identity of a V. Similarly, we can say that we have a W to V, we have a transformation S, linear transformation, and V to W, we have a transformation is equal to T. Now we have a, can say W to W, we can say the T of S, and this is nothing but equal to, we have a transformation from W to W. So this we have to denote it as a identity of a W. So clearly, if we have a T and S, if there exists a linear transformation S from V to W, if this condition is satisfied, then T is called as an invertible transformation, and S refers as its inverse. Okay, so we just say that, we can say that if we have to take two transformations, we have a T is one of the transformation. Then if there exists another transformation S, and we show that T of S is equal to identity and S of T is also identity, then we can say that T is an invertible transformation, and S refers as an inverse of a T is this. Okay, let's start with the one of the and now if this invertible transformation, and if this transformation is, this is a unique. Now we have, if T is a inverse, then it is a unique. So suppose we have to just take a, here is a S, we take a, there exists suppose S1 and S2 are two linear transformation from V to W. Satisfy the condition. Satisfy the condition is we have this condition. We have a T of S1 is equal to identity of W, and T of S2 is also is equal to identity of W, and then we have a S1 T is equal to identity of a V, and S2 T is also identity of a V. So we just say that if satisfy this, then this we have to assuming these two conditions. Then clearly we say that T of S1 is equal to identity of a W, and T of S2 is also identity of a identity W. Then we have a S1 T is identity of a V, and S2 T we have also identity of a V is there. So we take S1 and S2 be two linear transformations from W to V, satisfies these conditions. Both S1 and S2 satisfy this condition. So we just say that into this form we satisfy this condition. Now we have to show that this S1 is the same as a S2. So we just take a like this. So for any W belongs to W, so this means we have a S1 is from V to W. So we just say that, and then we can say that, and you can just say that we have a identity of we have this identity of a W. C means we can say that this is nothing but equal to T of S2. Here we can just say T of S2 is equal to identity of a W. So we just say that this S of W can be written this. So S of W, this S1 can be, I can write S1 of a W can be written as a S1 of a I of a W, and now I of a W is nothing but equal to T of this. So this can be written as S1 of T of S2 of W. Now because the T of S2 is equal to this, and now we use this condition. Now by using this we have a as S1 T, S2 W. Now we just check here you have a S of T1 or T2 R is equal to identity of a V. So this is nothing but is equal to, you have a I of a V, we have a S2 of W, and this is nothing but is equal to, we can say that S2 of a W, and this is true for all W belongs to the W. This means this implies that we can say that S1 is equal to, we have a S2. So clearly we can say that for any W belongs to this, we have to show that S1 is equal to S1 W is the same as a S2 W. So we can say that clearly is equal to this, satisfy this condition. So this means S1 is equal to S1. Now we prove that the inverse of a T is unique. The inverse of a transformation T is generally denoted by V into T inverse in this form. So by this method we can easily find, if we take as a any transformation is the inverse of naught, we take a T finding inverse, we take there exists one transformation, another transformation S. If we show that ST is equal to identity or TS is also identity, then we can say that if the inverse of is exists and this S is equal to inverse. For example, we take these two map R2 to R2, Txy is defined into this form. Now we have to take a T of S of, we have to take a xy, this can be written by the property of a composition function. We can write T of S of, you have a x and y, and x and y you have a defined into this form. You have a u minus v, so you have a write as x minus y, and then you have a y, and then T of is defined in the form of this. You have a x minus y plus y, and then you have a y, and this is nothing but is equal to, we can say that is a x and y, and this is nothing but is equal to, you have an identity map, identity of a x and y. So this means we can say that into this form. Now another way we can just check is what is S of T of xy, again by the property of a composition function S of T of xy, and this can be written as a T of xy can be written as x plus y comma y, and then we can write S comma this is nothing but is equal to x plus y comma, just a minute, this is x plus y comma y, and now S is defined into this form. So this is nothing but is equal to, we can write x plus y minus y and y, and this is nothing but is equal to, again xy is equal to identity of a x and y. So this is for all, we have for all x and y are the element of a R2. So this implies that we can say that Ts is equal to identity, and also here we have to, again for all this means S of T is equal to, we have a identity. Then we can say that the inverse of a T is exists, and we can find the say that S is nothing but is equal to is the inverse of a T. We have to just say that. Okay, this means we have to just calculating into this form. Okay, this is IV and IW, then we can say that clearly both the cases hold. So this means inverse, and then S is nothing but is equal to, we say that is a T of inverse. Okay, so we try to one more for this problem. We have to calculate the T of S of, we have to take any x, y, z is the, so let x, y, z is the element of a R3. Now T, by the definition of a composition function, we can say that this is nothing but is equal to, we have a S of x, y, z, and T of x, y, z is S x, y, z is equal to this form. We have a x minus y plus z, and then y minus z comma z. Now we operate a T, and T is nothing but is equal to x plus y. This is x and this is your y. So this is nothing but is, you can write in the x is equal to x minus y plus z plus y. Y is equal to, you have a y minus z, then y plus z. So you have a y is equal to, this is equal to y minus z and plus z, and then you have a z, and this is nothing but is equal to, we have a, this is cancel out all these things. So this means we can say that we have to getting the x, y, z, and then this is nothing but equal to, we can say that xi of xyz. For all xyz belongs to the R3, then we can say that in general we can say that T of S is equal to identity. Okay, so now we can show that clearly TS is equal to identity. This is, now we have to try to ST. So TS we have to already show that. Now we have to try to ST. So S of T we can write T of XYZ, and then this is equal to this. This means we have apply here. You have a, this is, you have a X, this is, you have a Y, and this Z as it is, X minus Y plus Z. So X plus Y minus Y minus Z and plus Z, then Y is, you have a Y plus Z minus Z, and then you have a Z still. Again Y, Z cancel out, then you have again X, Y, Z, and then this can be written as identity of a X, Y, Z. So we can say that ST is equal to identity. So both the cases we have to show that a TS is equal to identity and ST is equal to identity. Then S is nothing but is equal to T of inverse. So S is a inverse of a T in this case also. Okay, so now this complete the T is invertible and S is equal to T inverse. Now we have to just try state by the theorem, if T is the V and W be a vector spaces and T linear transformation, then T is invertible if and only if T is an isomorphism. Now we have show that T is an isomorphism, means this implies that T is 1 to 1 and onto, and if T is invertible, then we have T is invertible means we have to say that T is invertible if there exists a transformation S from W to V such that we can say that T of S is equal to identity, and we have a S of T is also we have an identity. So if we show that T is invertible, then we have these two condition is given, and with the help of these two conditions we try to show that T is 1 1 and onto map, and if T is 1 1 and onto map, then we have to show that there exists another map S and which is linear also, well defined and linear, then we can prove into this one. Okay, so let us start with this. Suppose T from V to V invertible, then there exists a linear map S from V to V such that S T is equal to identity of a V and Ts is equal to identity of a W. So we can just take into this form. This is our given condition. The St is equal to identity of a V and Ts is equal to identity of a W. Now we have to try to show that this T is a 1 1. So T is 1 1 means we show that T kernel of a T is equal to 0. So let V is the element of a kernel of a T, then T of V is equal to 0. If T of V is equal to 0, then we know that we have a S of T is equal to identity of a V. So we know that S T of a V can be written as identity of a V. We have a given. So identity of this is identity of a V, and now S can be written as a T of V, and this is nothing but is equal to, you can just say that or we just write into this form, this okay, leave this is equal to identity of a V. S of T by this operating in a T, then we can say the S of T of V is equal to 0. Now S of 0 T of V is equal to 0. S of 0 is always 0. We know that any linear transformation T of 0 is generally is equal to 0, and also we know that also we know that S T V is the identity of a V. This implies that we can say that this implies that a V can be written as an identity of a V, and this is equal to this St is equal to, this is equal to V, and also from here this thing is equal to 0. So by these two we can say that this is equal to 0. So this means we can say that we take a V is equal to 0. So what we show that we take any arbitrary element V belongs to the kernel of a T, and then show that this V is nothing is equal to 0. So this implies that kernel of a T is nothing but is equal to 0 subspace, then we know that the result is if we have a kernel of t is equal to 0 if and only if t is 1 to 1. So by this we can simply prove that the first part t is 1 to 1, then we can simply say that is equal to this. So this means we can say that this is a 0 subspace, so t is 1 to 1. Now we have to prove that this is a R2, this S composition t is a also is a t is onto. So because t is from V to W, then if you have a W belongs to the W, there exists some V belongs to the V. We have to show that t of V is nothing but is equal to W. If we show that t of V is equal to W, then we can say that range of a t is equal to V. So we can say that range of a t is equal to V. If range of a t is equal to, we have a W. So if we can say that range of a t is equal to W, then t is onto. Okay. So let W belongs to the W, because we have a t from V to W is a linear map. So we just say that, then now we have t of S W. Now we can just write into this form, and this is equal to this. So we show that t of S over W is equal to, you have a W. So this means we can say that there exists element V is equal to S of W. So this means if we take a W, then there V is equal to S of W in V, such that t of V is equal to, you have a W, because S of t, we just say that t times of a S of W, and now this is the element of a because S is a map from W to V. So this means if W belongs to the W, then S of W is the element of a V. So this is the S of W is the element of a V, means there exists some element of a V is the element of a S of W. So there exists an element V in V such that we can be written in the form of a S of a W, and we can say show that this is nothing but is equal to this is t of V is equal to, you have a this is equal to, you have a V. So this should show that we can show that by this t of V is equal to W, and then substitute the value for this S W is equal to V into this here, and then we can show that this is clearly this is t is an onto map. Okay, so now we complete proof that the t is clearly t is 1 1 and onto. So this implies that t is isomorphism. Okay, so now we have on 1 onto, so t is an isomorphism. Now we have to prove the conversal part. If we have a linear transformation T from V to V in isomorphism, then by the definition we can say that T is 1 to 1 and onto. Now we prove that if T is 1 to 1 and onto, so we just construct an inverse since T is onto, and now T is onto means every element W belongs to, there exists a, because T is from V to W, and if there exists a W belongs to the W, there exists some V belongs to the V, because T is onto, some V belongs to the V, such that T of V is equal to, you have a W. Now we have a T of V is equal to W. Now we define S is another map, and we have to define S is nothing but is equal to S of W is equal to V form. Okay, now we define this map S of W to V by S W is equal to V. So clearly first we show that this S should be a well defined, and also we show that this S is a linear, and then we can say that this is a this is the condition. So first we show that this is a well defined, and also we have to just, this is S is a well defined. We show that S is linear, and then we can show that ST is equal to identity and T of S is equal to identity if S is an isomorphism map. So by ontoness we can say that T of V is equal to W. So now we define a new map as W to V is the form we can write S of W is equal to V. So first we try to show that S is a well defined. So well defined because we have a T of V1 and V2 are the two elements, V1 and V2 are the element of a V. Then we have by the definition T of V1 is equal to W, T of V2 is also is equal to W. Now we just this implies that we can say that there exists a map S. So we have a S of T of V1 is equal to V2, but T of V1 is equal to V2 means T is 1 to 1, which gives that this is equal to V1 is equal to, we have a V1 is equal to, this means S is equal to is a well defined function. So S of W is equal to V, this means S this is a well defined function, because S of V we have to define in the form of a V, and then this we have to just take a V1 V2 and this form, that is TV and V1 is equal to V2. So if we take any these two elements, SW is equal to V1, SW is equal to V2. So we have to taking the S of W1 is equal to V1, S of W is equal to, we have to do V2. Then ultimately what we show that this means we can show is V1 is equal to, this is map is well defined. Now we show that S is a linear. If W1, W2, W, there is V1 and V2, because on two-ness T of W1 is equal to this, T of W2 is equal to this. By using the linearity of a T, we can write T of this T of V1 plus T of V2 can be written as a W1 plus W2. By the definition, S of W1 is equal to V1, S of W2 is equal to V2, and hence S of W1 plus W2 is equal to V1 plus V2, and then this is S of W1 plus S of W2. So we can just say that this by the linearity, this W1 and W2. So S of V1 plus W1 plus W2. So V1 plus V2 into this form. This. Okay. So we have to show that this is clearly is a now scalar multiple. T of W, T of V is equal to, we have a W. Then by the linearity of a T, this can be written in this form. So by S of W is equal to V, so S of a W, this is equal to, we have a S of alpha W is equal to alpha S of alpha W W-V, and then we can say that S of W S of W-V is equal to S alpha times of a S of W, because we can just show that S of W is the map of a W. So S of W is equal to V means W of a V, this is written in the form. So S of W is equal to alpha of a V, alpha V, and then we can say that S times alpha of W, as alpha W is equal to alpha times of a SW. So S is a linear transformation, and then we can say that because this S of WV here, W is equal to V, so V we have to substitute here, so we getting S of alpha times of S of W. So clearly we can say that we have this S is a linear transformation. Now we try to show that this identity. So W is equal to, by the V belongs to V, W is equal to the definition of S of W is equal to V. So we just write a composition map of a V, S of T of V, then S of a W, and now S of a W means we have a given is a V. V is nothing but is equal to identity of a V, is true for all V belongs to the V. So ST is equal to, we have a identity of a this thing. Similarly, we can prove that ST over we have a W, we can take a W, then this can be T of, you have a S of W. Now S of W is equal to, you have a T of V, and T of V is nothing but is equal to, you have a W, and this can be written as identity W of W. This is for all W belongs to the W. So we can say that clearly T of S is equal to identity of a W. So we prove both the conditions, that if we have a this means we have a T is an isomorphism if and only if there exists a map S from W to V such that T of S is equal to identity of a W, and we have to just say that S of a T is equal to, you have a identity of a V. So by this we have to just say that if this is happening, STS is equal to identity of a W and ST is equal to identity of a V, then we can say that this map T is an isomorphism. This is an isomorphism map. Okay, now we try to one problem. So this we can just say that this is hence T is a invertible. So by the definition of invertible, we prove that this is equal to this and this identity. So both satisfied by the definition of invertibility. We can say that T is a invertible. Okay, now we have a this problem. If a linear map T satisfies the condition T square identity of a plus identity is equal to 2, then prove that T inverse exists. And what is the value for a T inverse? So we try to, this means we clearly say that we know that using the this T inverse. So we have a Ts is equal to identity and we have a St is also identity. If we have to show that Ts is equal to St is equal to identity, then we can say that S is nothing but is equal to T inverse. By using this condition, we try to solve this. So we can start from here. T2 plus I is equal to T. This can be, we have to written in the form T square minus T is equal to identity, because is a minus identity is again is identity transformation. So the minus identity is equal to identity. So we just write this can be written as T times of a T minus identity is equal to, you have a identity map, and also we can say that simply is equal to, this can be this again written in the form of a T minus identity, T is equal to identity. So by these two conditions we can say that clearly T of T minus identity is equal to identity is equal to, we have a T minus identity of T. So by this St is equal to identity, S is equal to identity, then we can say that S is equal to T inverse, then we can say that T inverse exists, and T inverse is nothing but is equal to T of minus identity element. So this complete the proof of this solution. We complete the this solution clearly. Then this is we have to using this method by the previous theorem by the definition of a invertible transformation is saying that if we prove any transformation invertible, then we can find their existence transformation, linear transformation, and then such that this is giving you a identity element. So we show that this is clearly is a this is okay. Now we try to this way, this is in, and then on the other hand we have to get into this form. So clearly we can say that T inverse is equal to this satisfy, and this is a clearly we can say that this is hold the property of this thing. So I just complete the solution of this problem. Now I want to stop today's this class here. In the next class we discuss some another important properties of a composition of a map. That means if we take a like this, if we have a S and T are a two linear transformation, then what is the what about the inverse of a this composition of a transformation as T inverse, what one can say about the inverse. And now if we have a S and T are injective, then whatever the S is injective or T is injective, what about we can say about the composition of a transformation. So we discuss all this thing into the next class. So for this I have to stop today this is class here at this point. Otherwise, thank you very much for this.